It's late.
Yep.
The glow of your IDE is probably the only light in the room right now.
That familiar blue light.
Exactly. And you've been making API calls to these massive language models all day. You're building features, shipping code, basically treating the AI as this opaque black box.
It's a text-in, text-out machine.
Right. But if you're anything like me, there is this lingering itch in the back of your mind. You don't just want to know how to prompt the model.
You want to know what's actually happening under the hood?
Yeah, you want to know how an architecture with nearly 100 layers of neural networks doesn't just, instantly collapse under its own mathematical weight.
Because logically it should.
It really should. Welcome to the deep dive. Tonight, we're unpacking the load-bearing structural elements of the transformer. We're looking at the silent heroes of deep learning: layer normalization and residual connections.
And the stakes here really couldn't be higher for the architecture. It's incredibly easy to look at a system like Llama or GPT-4 and just assume that stacking more layers naturally leads to better performance.
Just add more compute.
Right, but mathematically, that is a complete nightmare.
Yeah.
Without these two specific, highly engineered stabilizing beams, deep neural networks are essentially untrainable.
Completely.
Anything past 10 or 20 layers diverges into total garbage within the first few hundred training steps. So our mission tonight is to decode exactly how these models manage to stack 80 to 96 layers and actually output coherent language.
So let's start with the first massive roadblock, which is just the fundamental impossibility of deep networks. A good way to visualize this is to imagine a microservice architecture with 100 independent nodes.
Oh, that's a great way to look at it.
Right. So you pass a highly detailed, nuanced JSON payload to the first node. By the time it's processed and forwarded through the 100th node without any data validation or structural enforcement along the way.
That payload has either exploded into completely unreadable noise or it's shrunk down to an empty object.
Exactly. That is your data passing through a deep neural network without stabilization.
Because every single layer in that network is applying a mathematical transformation. It's shifting and stretching the data space. And this leads us to the core technical villain of our story.
Internal covariate shift.
Internal covariate shift. To put it in developer terms, imagine you're writing a function that relies on an external API, but the schema of that API changes randomly every 5 milliseconds.
You're trying to hit a moving target?
Exactly. In a neural network, layer 5 is trying its absolute hardest to learn a useful transformation to find the right weights. But the shape of the data it receives from layer 4 just keeps changing.
Because layer 4's weights were just updated during the training step.
Right, and layer 4 updated because layer 3's outputs shifted.
Wow.
It is quite literally turtles all the way down.
Okay, let's unpack this. Because that cascading instability is the exact mechanism behind the absolute terror of deep learning, the vanishing or exploding gradient problem.
A total nightmare.
For anyone who has ever fired up a PyTorch training loop, you know this pain. Epoch 1 looks fine. But by step 400, your loss function suddenly outputs nan.
Not a number.
Yep. You update a weight in layer 1 by a tiny fraction, and by layer 50, that change has compounded into an enormous network-destroying wave of floating point overflow. So, how do we fix the scale?
We standardize.
Enter our first fix. Let's look at the 2015 breakthrough, batch normalization.
Right, so the idea behind batch norm was to standardize the outputs after each layer so they have a zero mean and a unit variance. Think about it like normalizing a data set in a relational database.
Or managing floating point scales in traditional software architecture to prevent underflow.
Exactly. You look at the entire batch of data passing through, you compute the statistics, and force the distribution into a predictable range before passing it forward.
And for computer vision applications, batch norm was an absolute revelation.
No, game-changing.
But for language models, for the text you are generating right now, it is a structural disaster.
Why is that? Batch normalization assumes all the examples you're processing together in a batch share a meaningful statistical relationship. Natural language sequences just don't.
Right. They're incredibly variable. You might have a batch where sequence 1 is a 5-token user prompt, sitting right next to sequence 2, which is a 200-token system prompt.
Exactly. Computing an average across those different positions creates completely messy statistics. The meaning of a token heavily depends on its specific position and context.
So normalizing across different positions in completely different sentences introduces statistical noise rather than stability.
But the real deal breaker for you, the software engineer implementing this in production, is the train-test mismatch during inference.
Yeah, inference.
Yeah. When you deploy an autoregressive language model, you are generating one single token at a time. There is no batch.
It's just you and that single token.
Right. You cannot compute batch statistics on a batch of one. The traditional workaround was to rely on running averages saved from the training phase, which introduces a massive source of error and fragility into the deployment pipeline.
Which prompts a crucial pivot. In 2016, researchers Ba, Quiros, and Hinton introduced layer normalization.
A brilliant shift.
If batch norm is trying to standardize across the entire database table, layer norm is looking at a single row and evaluating it purely on its own internal consistency. It normalizes across the feature dimension.
Mathematically, this is a profound shift. Let's say a single token in your transformer is represented by a vector of 768 values.
Okay.
Layer norm looks only at those 768 numbers. It computes the mean and variance of just that specific token's features and normalizes them independently.
So it completely ignores what the rest of the batch is doing.
Exactly. Token 47 in sentence 3 is normalized the exact same way every single time, whether the batch size is 1 or 1,000.
That solves the autoregressive inference problem beautifully. You're generating one token, you normalize its features, and you move on.
Smooth and consistent.
But optimization is the name of the game in AI. We want faster compute, lower latency.
Yeah.
In 2019, the community adopted a brilliant modern hack, RMS norm, or root mean square normalization.
RMS norm is one of my absolute favorite optimizations because it's ruthlessly pragmatic. Researchers analyze layer norm and realize that the mean centering...
Calculating and subtracting the average of those 768 values.
Right. They realized it was computationally expensive and actually wasn't doing much to prevent the network from exploding. Shifting the data doesn't stop floating point numbers from compounding into infinity.
So what was doing the actual heavy lifting?
The real magic was strictly in controlling the variance, the scale of the activations. So RMS norm just drops the mean centering entirely. You don't subtract the mean, you just divide the values by their root mean square.
Meaning you shave off an entire sequence of compute operations per token per layer.
Exactly. And when you're running billions of these operations during a single training step, dropping one mathematical step translates to huge, measurable speedups. It's strictly better engineering.
It really is.
You get the exact same stabilization quality with significantly less compute overhead. If you pull down the source code for leading models today, Llama, Llama 2, Mistral, and look at their neural network definitions, they are all utilizing RMS norm. It has become the undisputed industry standard for efficiency.
Here's where it gets really interesting, though. We have this optimized normalization tool, but where you physically place it in the code architecture changes everything. This is the battle of pre-norm versus post-norm.
Oh, this is a huge architectural detail.
In the original 2017 attention is all you need paper, they used post-norm. They applied the normalization function after the attention and feed-forward sublayers. Imagine a major high-speed interstate highway, and right in the middle of all the lanes, you build a massive toll booth.
Just blocking everything.
Yeah. Every single piece of traffic, every piece of forward data, every gradient flowing backward during training has to start and pass through that normalization toll booth.
And traffic backs up immediately. The gradients, which are the vital signals telling the network how to learn, get distorted every time they pass through that bottleneck.
So the community shifted to pre-norm. In our highway analogy, you remove the toll booths from the main interstate and you only put them on the exit ramps.
I love that analogy.
If you want to take the exit to the attention sublayer, you go through the normalizer. But the main highway remains completely wide open. If you open up the Hugging Face implementation of any modern LLM, you will see the normalization function called before the attention block, not after.
What's fascinating here is the impact this architectural tweak has on training dynamics. By keeping that main highway, the residual stream, completely clear, the gradients can flow all the way backward from the final loss calculation to the very first layer.
Without being squashed or distorted by normalization operations.
Exactly. Pre-norm makes training significantly more stable. It makes the model far less sensitive to your choice of learning rate, and the entire system converges faster.
So even if post-norm theoretically offers a tiny bit more regularization,
the training stability of pre-norm is so overwhelmingly beneficial that it is a non-debate in modern engineering.
Okay, so we've built a clear highway and managed the scale of the traffic on the exit ramps, but we need to examine the highway itself. That brings us to the second pillar of deep network stability, residual connections.
Essential.
This concept was borrowed from computer vision, specifically the ResNet architecture from 2015. To understand why this is so brilliant, think about a manuscript that needs to be edited by 50 different editors in sequence.
Okay.
In an old-school neural network, every editor is handed a blank piece of paper. They have to read what the previous editor wrote and then retype the entire manuscript from scratch, incorporating their changes. It is incredibly lossy.
Because the network is forced to learn how to perfectly recreate the input just to pass it along.
Yeah.
For a neural network initialized with random weights, perfectly passing information forward through 50 layers is notoriously difficult. Mistakes compound. Information degrades.
But with residual connections, the equation shifts to output equals x plus f of x is the input, the manuscript. You hand the manuscript to the editor, and you just ask them to act as a copy editor.
It's marking it up.
Yeah. Take a red pen, make some markup, add a few notes in the margins, that is the f of x. If a particular layer looks at the data and has absolutely nothing to add, it doesn't have to retype the whole thing, it just does nothing. F of x equals 0.
The original manuscript, X, passes through completely untouched.
Exactly.
And this brings us to the mathematical intuition that absolutely saves the network during backpropagation. When you train a neural network, you use the chain rule from calculus to compute gradients.
Right.
In a standard network without residual connections, you're continuously multiplying the gradients from every intermediate layer together. Imagine multiplying a number slightly less than 1, say 0.99, across 50 layers.
You get 0.99 to the 50th power.
Which drops to about 0.605. If the gradient is 0.9, it drops to 0.005. The signal just vanishes into nothingness. The early layers learn absolutely nothing because the training signal never reaches them.
But the residual connection alters the fundamental math of that backward pass.
It does. When you take the derivative of that output, x plus f of x, during backpropagation, that x becomes a hard one. I want you to visualize that one as a guaranteed bypass lane for the gradient.
A dedicated lane just for the signal.
Yes. No matter what the rest of the derivative evaluates to, even if that layer-specific gradient is 0, there's always a direct one path for the training signal to flow backward. It bypasses the vanishing gradient problem entirely.
That's incredible.
This single mathematical addition is what allows a model like GPT-3 to cleanly hit 96 layers, and for information to propagate flawlessly from the end of the network back to the beginning.
You literally just add the input to the output. It is stunningly simple. But how do these two systems, layer norm and residual connections, actually function as a unified team?
They're highly complementary.
The source material uses a great analogy of a massive relay race with 100 runners. The residual connection is the walkie-talkie connecting every runner directly back to the coach. That is the clear gradient signal.
No matter where you are on the track, you hear the coach's instructions perfectly.
Exactly. And layer norm is the hydration station at every single handoff. It keeps the activation values sane. It ensures every runner starts their leg of the race in perfectly stable condition. One solves the communication bottleneck, the other solves the physical scale.
And they absolutely depend on each other. If you implement residuals without normalization, your values just accumulate and explode. 96 layers of unchecked addition will overflow your variables instantly.
And if you have normalization without residuals,
Your gradients still vanish as they grind through layer after layer of complex transformations. Together, they create a perfectly balanced, virtuous cycle. Though, for the software engineers listening who are actually going to implement this, there's a very specific initialization problem you have to watch out for.
the cold start problem.
Yeah, when you initialize a network, your weights are random. Because of the residual connections, every layer is adding its output to the mainstream. If you have n layers, the magnitude of that residual stream grows by roughly the square root of n.
So for a massive model, that means your stream is blowing up by a factor of maybe 10x on the very first forward pass.
Before any training even happens. The implementation trick here is to scale the initialization of the final linear layer in every residual block by 1 over the square root of 2n.
Right.
This forces the early contributions to be tiny, keeping the stream mathematically well-behaved while the network gets its bearings. GPT-2 used this exact trick, and variations of it are crucial for everything built today.
So we have our clear highway, we have our toll booths on the exit ramps, we have our 1 over root 2n initialization to handle the cold start.
If we connect this to the bigger picture, it fundamentally changes how we conceptualize deep learning. For decades, the standard developer mental model for neural networks was a pipeline.
Layer 1 does its job, passes a completely transformed object to layer 2, which passes it to layer 3, and so on.
But the residual connection gives us a radically different paradigm, the residual stream perspective.
This flips the traditional mental model of how a neural network operates. It's not a pipeline, it's a shared workspace.
Think of the residual stream as a single, continuous, shared memory bank that runs from the very first token to the final output.
Mm.
The layers, the attention heads, and feed-forward networks, they're not sequential stepping stones. They're independent workers standing around this shared workspace.
Reading and writing.
Exactly. Layer 3 reads from the stream, computes some specific syntactic relationship, and writes a tiny update back into the stream. Layer 50 comes along much later, looks at that exact same stream, and can directly access the information that Layer 3 deposited.
The original input is never destroyed, it's just continuously annotated.
Right.
It's not an assembly line where the car frame gets permanently hidden by the body panels. The entire history of the sequence's processing is available in that stream.
It's a beautiful way to think about it.
So what does this all mean? Why did we spend the night digging into pre-norm routing, PyTorch loss functions, and the bypass lanes of backpropagation? Because when you are building, tuning, or debugging these massive models, understanding that they are built on these two delicate stabilizing beams changes how you view their entire architecture.
It's not just a black box anymore.
Exactly. When a model converges flawlessly, it's not magic. It is heavily engineered stability. It is the result of researchers fighting tooth and nail against internal covariate shift and vanishing gradients.
And understanding that structure opens up entirely new ways to manipulate these models. This raises an important question, one that researchers are actively exploring right now. If the transformer is ultimately just one shared workspace, a single residual stream where layers just read and write small updates, what happens if we break the rules?
Like what?
What happens if we force a model to skip certain layers entirely during inference?
Oh, like dynamically dropping layers on the fly to save compute?
Exactly. If the representation in the residual stream is robust enough, and layers are just adding minor edits, could you analyze the stream at layer 40, decide, you know what, this text generation is simple enough, and just skip the remaining 40 layers?
Or would the whole fragile ecosystem collapse because layer 70 was secretly relying on a highly specific edit from layer 69?
That is the million-dollar question.
That's a fascinating thought experiment. If it's truly a shared memory space, maybe those middle editors aren't always necessary for an easy manuscript. Something for you to mull over the next time you're watching a language model stream tokens to your terminal. Think about the massive gradient highway, the precise RMS norm scaling, and the shared residual stream making every single word possible.
There's a lot going on under the hood.
There really is. Thank you for joining the conversation tonight. Keep questioning the abstractions, keep digging into the math behind the machine, and we will see you on the next deep dive. Have a good night.